Today I'm presenting you the results of my latest work, supervised by Professor Vasile, titled Autoencoder-based Thermospheric Density Model for Uncertain Quantification and Real-Time Calibration. This presentation is structured as follows. First, I will outline the context of this work and the associated motivations for it. Then, I will discuss two machine learning-based reduced order modeling techniques, making use of autoencoders. From there, I will present you a simple case study, the chaotic Lorentz system, to demonstrate the capabilities of the proposed methodology. After that, the most relevant result of this work, the modeling of the thermospheric density field, will be discussed and results will be given. Before concluding, I will expand the methodology, connecting the results of this work with previous works we have recently published, dealing with data-driven reconstruction of governing equations. Finally, conclusion and additional recommendations for future works will be discussed. So, as probably everyone in this audience knows, in the context of the so-called new space, low Earth orbit is nowadays characterized by an unprecedented increase in space traffic. The clearer example of this is the launch of mega constellations. Additionally, we notice how the dynamics of LEO satellites is strongly influenced by atmospheric drag. This force is also the largest source of uncertainty. Dealing with motivations for this work, accurate orbit determination and uncertainty quantifications are required to perform a conjunction assessment and collision avoidance. More in general, the increase in space traffic motivates the ability to efficiently track and catalog objects. So, because of these reasons, it becomes necessary to build an existing atmospheric density model to construct a gray box model of the dynamics and efficiently perform real-time calibration and uncertainty quantification. So, bringing it all together into the goal of this work, we aim at using autoencoders to obtain a reduced order representation of the dynamical system governing the evolution of the thermospheric density field. Let's start by describing what autoencoders are. They are a family of neural networks which are trained such that their input is copied into their output. Because of their usual structure, in which inner layers of the network are characterized by a small number of neurons compared to the input and the output, as you can see in the image on the right, the Z vector associated to the so-called bottleneck of the network is a latent compressed representation of the input vector X. For people familiar with dimensionality reduction, the figure on the left should clarify the relation between autoencoders and, for example, proper orthogonal decomposition. When using only one layer for the encoder and the decoder, and using linear activation functions to construct them, the procedure is equivalent to the single value decomposition from which the matrices U and V arise. A subcategory of autoencoders can now be introduced. Convolutional autoencoders perform the same task of standard autoencoders, but making use of a slightly different architecture. The layers of the network perform the convolution operation, as given in the figure. For the compression of the density field, this family of autoencoders will be used. The main reason is that the convolution operation takes into account the relative position of the measurements. And this is ideal for modeling partial differential equations in which local interactions drive the evolution of the field. So let's now start dealing with the chaotic Lorentz system. The system has been chosen because it's both chaotic and strongly nonlinear, two features shared with the dynamics of the atmospheric density field. The set of equations governing the evolution of the three-dimensional system are given in the slide. Now, since we're interested in observing a high-dimensional field to be compressed with autoencoders, we construct an analytical mapping going from R3, the physical space, let's say, to R128, so that we can assume that the true three-dimensional dynamics is not directly observed. This mapping is constructed making use of Legendre polynomials evaluated along a uniform grid. The components of the U vector are given in the bottom equations and are made of 128 evaluations of the nth Legendre polynomial. We will consider two different mappings, one linear and one nonlinear, given respectively by x1 and x2. And in the latter, we consider cubic terms added to the linear mapping. Now, we can consider different initial conditions of the Lorentz system in order to obtain a number of 128-dimensional observed trajectories. Such trajectories are divided into training and validation trajectories. This is usually done in the context of neural networks. The idea being that neural networks are trained against the training data, and at the same time, their performance is assessed against validation data. So, dealing with linear mapping, the linear mapping given in the previous slide, we make use of a linear activation function to construct our autoencoder. Once the autoencoder is trained, we can compare one of its inputs taken from the validation data and compare it to the decoded trajectory. The third figure represents reconstruction error, that is the mismatch between the output and the input of the autoencoder. We can now look at the same results for the case in which the mapping between R3 and R128 is nonlinear. In order to compress the associated data, we need to adapt the structure of the autoencoder, which is built making use of 5 layers and substituting the linear activation function with the hyperbolic tangent function. The same results as before are given in the figures. And in this case, you can see that the reconstruction error is even smaller than before. It's in the order of 10 to the minus 5. So let's now focus on what happens inside the autoencoder. In fact, when using autoencoders, and in general when dealing with dimensionality reduction, the interesting result, together with the ability of the autoencoder to reconstruct the original data, are compressed data themselves. Once the network is trained, we can look at the conceptual steps associated to the reconstruction of the reduced order trajectory. We start from the three-dimensional Lorentz system given in the first figure. Via the analytical mapping, we go to R128 and get the observed trajectory, used as an input to the autoencoder. Finally, we can plot the trajectory associated to such reduced order representation given in the right. We now show the plots associated to the convergence during training. The figure on the left is a bit anomalous in the sense that the validation loss is really small already from the first epoch. This is because a linear activation function has been used. The figure on the right shows a more standard convergence, let's say. Let's now shift to the more practical problem in which we aim at modeling the thermospheric density field. For this, we make use of the HASDM model data. When we first formalized this work, we started from the DTM 2013 model dataset, which are shared by the European Space Agency. But we ended up using the HASDM model instead because of the time interval covered by the available data, going from January 2000 to December 2019. Such data cover more than one solar cycle and are thus representative of the overall behavior of the density field. This is particularly relevant for extrapolation performance. So the available data have a temporal resolution of 3 hours and a spatial resolution of 10 degrees in latitude, 15 degrees in longitude, and 25 kilometers in altitude, going from 175 to 825 kilometers. An example of the density field at 400 kilometers altitude is given in the figure. So, as previously stated, the dynamics of the observed field is associated to a partial differential equation in which local interactions are relevant for the evolution of the density field itself. And because of this, convolutional autoencoders, and in particular three-dimensional convolutional autoencoders, are used. This means that the input is a 3D tensor associated to polar coordinates. The network is now made of 4 convolution and 2 fully connected layers. In the figure is again shown how the density field prediction will be performed using its compressed representation, not the original state observed, let's say. Dealing with hyperparameters, after tuning, the latent state size has been set to 32. The rectifier activation function has been used in all the layers. And once training is done, we can test the performance of the autoencoder on a given dataset. For example, the data associated to 175 kilometers altitude on the 1st of January 2000 at midnight. You can see how the reconstructed field matches the behavior of the input field. The absolute error field is represented in the figure on the right. We show again proof of convergence using different batch sizes. It is shown how bigger batch size leads to a smoother convergence. You can see the figure on the right. So let us now expand a bit around the shown results, briefly discussing symbolic regression. Reduce all the model data of the autoencoder can be used to generate expression and obtain best fitting differential equations governing the spatial and temporal evolution of the density field. Now, previous works trying to model the evolution of the thermospheric density made use of dynamic mode decomposition, which leads to an estimation of a linear dynamics associated to available data. While linearity may be a desirable feature in some contexts, it is a big limitation in order to estimate the true dynamics, let's say, best fitting dynamics. So symbolic regression does that and leads to nonlinear expressions. Moreover, symbolic regression can be coupled with sparse regression to reduce computational costs and avoid overfitting. In the figure on this slide, you can see how the Latin representation of the input of the autoencoder is fed into the given equation. Once the explicit formulation of the system is available, it is possible to make use of available tracking data to perform real-time calibration of the density field, and also implement uncertainty propagation techniques to take into account the non-Gaussianity of the probability density functions, leading to an accurate computation of the probability of impact. Sorry. Other recommendations for future work include the use of a spherical convolutional neural network to better deal with the availability of density data. Also, regression algorithms will be developed in order to take into account space weather, and geomagnetic activity as control inputs. Space weather forecasting algorithms will be developed to extrapolate results in the future. And finally, the application of a similar methodology for the reconstruction of the wind field should be investigated. For example, considering the FPI and SDI observations and the wind data associated to the ICON mission. In conclusion, convolutional autoencoders constitute a promising nonlinear reduced order modeling technique to be used in the context of atmospheric density modeling. As discussed, artificial intelligence techniques can be used to obtain an explicit nonlinear differential formulation of the governing equations. And finally, an explicit knowledge of the dynamics enables one to perform real-time estimation and uncertainty quantification. Here you can find some more references used in the production of this work. And again in this slide, if you're interested. And finally, here you can find my email and the acknowledgement to my research network, which supported this work. So I look forward to for your questions, both in my email address and now. Thank you very much.